Hey folks, and welcome to another edition of Tech Talks with Celestial Systems. I'm your host, Richard Wong, and with me today is Logan Selby, co-founder and president of DataShapes. How are you today, Logan?
Good, Richard. Thanks for having me on. I appreciate it.
Yeah, thanks for coming on. So I guess for those that don't know, and myself included, can you tell us a little bit about your background?
Yeah, so I spent most of my career in the DoD, mostly in the intelligence community. So I spent a lot of time working strategic intelligence missions overseas. So got the opportunity to live in Europe for several years. Spent a lot of time in Ukraine and the Baltics and
Oh,
those
nice.
fun places over the years. Still an active reserve officer. So currently I'm the lead for autonomy and robotics for an organization called the 75th Innovation Command. So we're a reserve direct reporting unit to Army Futures Command. So in that capacity, I do a lot of the industry outreach and academia outreach for the 75th under Army Futures Command for really anything autonomy or robotics related. But I transitioned out of full-time government service in 2018 and went into Fortune 500 for a little while, and then worked at another small startup and came across DataShapes and started advising and came on full time in January of 22. So
Nice.
that's, I guess, experience wise on the academia side. I have a PhD in autonomous systems. So hence the robotics connection there. But
Yeah,
I have a master's degree in data science and applied machine learning as well. So I
that's
don't I
awesome.
don't like to call myself a data scientist. But I do have the piece of paper that says it. So but
Nice.
yeah, that's a little bit about me.
Thanks for that, Logan. So you're the president of DataShapes. For those that don't know, can you tell us a little bit about that company?
Yeah, so DataShapes, we focus on what we call signal and waveform intelligence. So really, it's interesting. So if you think of a waveform, anyone that can think back to like science class from elementary or middle school, you think of like
Okay.
a wave going across the screen. So really, anything that can be visually represented as a waveform, that's what we ingest with our AI platform. So anything from a cardio beat is a waveform, audio from music to radio frequency, vibration, acoustic, UV, you name it. Anything that you can visually represent as a waveform, our platform can ingest it and then pull intelligence out of the waveform.
Okay. So waveform being sort of, what comes to mind for me is like something cyclical. Is that right?
It,
For
it
it to
can
for
be,
it to create
yeah.
a wave? Yeah.
It can be, yeah. So something that has a unique signature, but it can be consistent. But it can be there are times where it could be something non-consistent as well. So like especially in the DoD world, we have a lot of waveforms that we're analyzing that are burst waveforms. So it could just be
Hmm.
a small little burst that is associated with something that our platform would then be able to recognize and give the end users some intelligence about it.
Okay. What are some of the applications in various fields?
Yeah, so right now we're doing a lot in defense, so mostly in electronic warfare and signals intelligence. And those applications range from being able to identify or classify the type of signals that are being admitted towards a U.S. Piece of machinery. So it could be somebody trying to jam or spoof something, or it could be
Okay.
somebody trying to do something nefarious. We will take that signal, analyze it, and be able to give the end users, some more granular level intelligence about where it's coming from, what it is, what it's doing, who's it's associated with, and then try to correlate it to any past event where that's occurred. And that's all in. We can do it all in real time, on the piece of machinery that's being targeted. So that's really the critical piece that we're solving is we're doing it in real time.
Oh, wow. Okay. And what are I guess, the key variables you're looking at when analyzing this data?
We're really looking for as the waveform is ingested into our platform, the way our machine learning works, it actually takes measurements, so granular measurements of the waveform as it's being ingested. We call them metrologies, but taking
Okay.
small measurements of that waveform, and then we're actually appending metadata to it in real time as well. So while we're doing that, we're looking at those measurements to associate it with either a known signal or an unknown signal, and then labeling that in real time, providing end users that real-time analytics behind it too, saying, hey, this is this signal, this is that signal, this is differentiated between these two signals, because times when you're getting hit with a lot of waveforms in some type of domain, there's a lot of noise. There could be a lot of simultaneous signals happening at one time. So we're able to differentiate between those different signals and provide the end user intelligence about what they are, where they're coming from, who they could potentially be coming from as well, who they're associated with.
Okay. And I guess how does an end user extract like meaningful insights from it then, like, or actionable insights?
So we
What are some
provide
examples?
it in our platform. So we have a pretty robust UI we call Waveshaper. And so the waveform that's being collected and analyzed comes into Waveshaper. The analyst can then play with the waveform in real time, I guess, and do some search, do some run some analytics, run some additional measurements on it. Once it's learned, so our software actually learns the waveform in real time as well. So we're using zero to few shot learning as well as a part of it. And so it learns the waveform, and then it will recognize that waveform anytime they're forward. But it'll also, since we're appending metadata to it, it'll also let you query any waveform that's happened historically. So, a good use case would be, if you're, say you have some sonar type sensors off the coast of California.
Yeah.
And let's say you've been collecting sonar data for 10 years. You would run all that sonar data through our system. We would learn it in real time. We would append all that metadata to it from the measurements and things that we've taken. And then we could deploy our software real time on that sensor. So then anything coming in, we can identify any correlations from that past historical data and allow you to query it as you learn new signals along the way, and it opens up the aperture for a lot of analysts to explore real-time data versus historical data and make some of those correlations.
Okay, that's cool. Yeah, I'm just thinking like other, like, besides defense, other applications that
Sure. So we do a lot of work in the music space as well. So
makes sense.
audio, music is a waveform as well. So the way it's applied there is very similar to the way we apply it in the defense space. But we're using it for copyright and artist attribution. So which is really interesting.
I've heard this beat somewhere before, right? And then you kind of run it through. Yeah.
Yeah. So we've worked with some of the music labels, some organizations that are trying to thwart some of the copyright issues in the music space to give artists their due. And so it's very powerful at being able to understand transformations of songs. So say you're a social media influencer and you upload a Taylor Swift song. But you've altered it in a way that common software out there can't tell the difference. So you've like layered static on it, or you sped it up, you slow it down, change the pitch. So those are ways that folks trick algorithms today. So we can actually see through that and understand if there's been a transformation made to an original track.
Wow. Okay, that's really interesting use case, Logan. And how do you detect anomalies in waveform data? What kind of techniques do you typically use?
Yeah, so we have one piece of software that we call Infinite Loop, and so Infinite Loop is a self-learning anomaly detection. So it is a true self-learning piece of software. So it's deployed on the edge without any training whatsoever. It learns a baseline of what's normal in the waveform environment, and then it will alert on anything that is anomalous compared to that baseline. So we call it continuous learning. But as an end user, you can set parameters to it if you want. So you could come in and say, hey, I want to know a baseline. My baseline is 7 days, or my baseline is 365 days. You can set that, and then if there's any anomalous behaviors that occur, inside those parameters, we would alert you. Or if you want to go strictly self-learning, you would just deploy it without any parameters, and then we would consistently learn and understand if there's any differences happening to whatever use case you're applying it to. So a lot of our end users are looking to apply it to predictive maintenance type issues or sensing type applications. A couple of the big use cases that we're working with now is in space. So putting Infinite Loop on an actual satellite, so it learns what's normal from a satellite in orbit, because there's a lot of issues that could occur both with like electromagnetic interference, or even jitter over time for as you're maneuvering a satellite. It could experience jitter. So understanding why that's happening and when it's happening and alerting on that in real time is critical to ensure you're maintaining appropriate operations for your asset.
Wow. Okay. I mean, it sounds like some pretty important use cases.
Yeah.
Um, yeah, and I guess we talked about the applications in defense. We talked about the applications in music. I guess kind of in that same vein, where do you see DataShapes going in the next 5 years?
Sure, sure. So, like I said, our plan now is we're trying to stay pretty strict in defense, with doing a little bit in music. Over the next 5 years, we see ourselves pivoting to some more commercial applications. So we are having conversations with folks in the energy market. We believe there's a lot of opportunity there on the waveform side, especially in so energy itself, and then in the spectrum, like spectrum awareness on the commercial side as well. So understanding what's happening in and around various buildings and communities and things when it comes to waveforms.
Mhm.
So those are two areas that we definitely look at opening up in the future. Healthcare is another big one. As I
Oh
mentioned
yeah.
earlier, cardio being a waveform. We
Mhm.
have done some work in healthcare in the past. It was mainly on the big pharma side. So we see ourselves maybe pivoting to more strictly healthcare on maybe AI solutions for devices and things like that as it pertains to waveforms.
Okay. Uh, I mean, that's great, Logan. You briefly mentioned AI. Can you tell me a little bit about how that factors in with what you guys are doing? I know you're working with like sort of large amounts of data. How does how does data shapes differ from the sort of the buzzword of AI in this day and age?
Sure, sure. Yeah, a lot of people. There's a lot of talk around large language models and just what we call conventional AI, so large
Mhm.
neural net based solutions. And so you really have your two buckets today. So one being vision applications, so computer vision, people wanting to use images and video, and then organizations wanting to use the language models, large language models, or NLP and things like that. We're kind of a third offset. So we don't use large neural net based solutions for our products. Ours, they are proprietary. So we have a handful of patents on our technology, and we've created it over the last decade or so. So our engineers have taken traditional machine learning algorithms and then kind of taken them to another level. So and that's where we've built our patent art around, is essentially that concept. But since we're doing that, a lot of these other two buckets, image and large language models, they require a lot of compute. So that's one of the I would say cons for those types of techniques. They're great. I mean, they solve a
Mhm.
lot of problems, they do a lot of things, and they have their place for sure. We're not a panacea. We solve a very niche problem, but
Right.
the way we do it requires very very low compute. So we've scaled applications of ours down to at the kilobit level, so they can run on microprocessors,
Wow.
low level OSs on sensors, and then we've scaled it all the way up to our enterprise applications that we use that are SaaS based as well. So we use that traditional machine learning kind of I would call it. Souped up in a way that enables our use cases that I mentioned, but that can operate at a very low compute level.
Okay. I mean, that sounds really awesome, Logan. Yeah. I mean, I think, yeah, especially with the sort of the whole AI craze now, like, I mean, case in point, like the NVIDIA stock, right? Where people are needing more computing power and all that kind of stuff, right? But it's good to hear that you guys can scale it as needed. Yeah.
Yeah, no, it's a big selling factor. Everybody wants, in the DoD we call it SWAP, so size, weight, and power. So everybody wants a smaller SWAP. So
Yeah.
we're looking to solve that problem. Building solutions that can analyze waveforms on handheld devices that people in the field can use, putting this on small satellites that can exist in low Earth orbit, things like that, just to make it an easier process, lower weight, lower size, those type of things.
I see. Awesome. Well, I mean, thanks a lot for hopping on today with us, Logan. It was really good to chat with you.
Yeah, thanks again. Thanks for having me.
Yeah. And I mean, thanks again for hopping on, and yeah, have a great week, Logan.
All right, you as well. Bye-bye.
Yeah. Take care.